Determine whether the sequence converges or diverges. If it converges, find the limit. Let's take a look at example 1. Suppose a sub n is equal to 4 to the n divided by 1 plus 9 to the n. I'm going to apply the squeeze theorem. So notice, 4 to the n over 1 plus 9 to the n is greater than or equal to 0 and less than or equal to 4 to the n over 9 to the n, which can be written as 4/9 raised to the nth power. So I want to make sure we understand this inequality right here. Now, notice, if I take 1 plus 9 to the n, that's absolutely greater than or equal to 9 to the n, right? Now, if I take the reciprocal, so in other words, if I take 1 over 1 plus 9 to the n, that has to be less than or equal to 1 over 9 to the n. So this is going to take a lot of practice, okay? And all we have to do from there is multiply both sides by 4 to the n. So 4 to the n over 1 plus 9 to the n is less than or equal to 4 to the n over 9 to the n. And that's where that inequality came from. And again, 4 to the n over 9 to the n can be written as 4/9 to the nth power. The limit as n goes to infinity of 4/9 to the n is equal to 0, because remember, the absolute value of r is equal to 4/9, and that's less than 1. By the squeeze theorem, we can say that the limit as n goes to infinity of 4 to the n over 1 plus 9 to the n is equal to 0, and we can thus conclude that this sequence converges to 0. And that's example 1. So let's take a look at example 2. Suppose a sub n is equal to 2n minus 1 factorial divided by 2n plus 1 factorial. Recall, n factorial is equal to n times n minus 1 times n minus 2 times 3 times 2 times 1. But look at what I'm going to do. I'm going to block off these factors here. And so I'm going to rewrite this as n times n minus 1 factorial. Notice that n minus 1 times n minus 2 times times 3 times 2 times 1, that's just another name for n minus 1 factorial. So again, n factorial can be written as n times n minus 1 factorial. We need this. So if we look over here, the limit as n goes to infinity of a sub n is equal to the limit as n goes to infinity of 2n minus 1 factorial divided by 2n plus 1 factorial. But this can be written as the limit as n goes to infinity of 2n minus 1 factorial divided by 2n plus 1 times 2n times 2n minus 1 factorial. And if you notice, the 2n minus 1 factorials end up going away. It reduces to 1. And so what we have left is the limit as n goes to infinity of 1 over 2n plus 1 times 2n. But this is equal to 0. And we can thus conclude that this sequence converges to 0. That's example 2. Let's take a look at example 3. Suppose a sub n is equal to n squared divided by the square root of n to the third plus 4n. The limit as n goes to infinity of a sub n is equal to the limit as n goes to infinity of n squared divided by the square root of n cubed plus 4n. And so what I'm going to do is factor out an n to the third within the radical. And when I do that, I get the limit as n goes to infinity of n squared divided by the square root of n cubed times the quantity 1 plus 4n over n cubed. couple of comments. Now, notice on the last line, we write the limit as n goes to infinity of n squared divided by the square root of n cubed times the square root of 1 plus 4 over n squared. So I broke up that product. Now, one comment is this. The square root of n cubed is equal to n raised to the 3/2. If I take n squared over the square root of n cubed, this is equal to n squared divided by n to the 3/2. But remember, 2 minus 3/2 is 1/2. So this can be written as n to the 1/2, which is equal to the square root of n. Okay? And if I take 4n divided by n cubed, this is 4n divided by n times n squared, right? N times n squared is n cubed. The n's cancel, and we get 4 over n squared, and that's where I get this piece. Now, where do we go from here? This is equal to the limit as n goes to infinity of square root of n divided by the square root of 1 plus 4 over n squared. And this is indeed equal to infinity. Because remember, as n gets large, 4 over n squared is going to 0. And so what you essentially have is infinity divided by the square root of 1. And what that tells me is that this sequence diverges. When you get infinity, that's just a fancy way to say that the limit doesn't exist. That's example 3. Let's take a look at example 4. A sub n is equal to n to the 1 over n. Set y equal to x to the 1 over x. Take the natural log of both sides. So the natural log of y is equal to the natural log of x to the 1 over x. And incidentally, we can write this as 1 over x by the properties of logs times the natural log of x over 1, if you want, which is written as natural log of x over x. The limit as x goes to infinity of natural log of x over x, right, by L'Hopital's rule, right, LH, this is equal to the limit as x goes to infinity of 1 over x over 1. But as x gets bigger and bigger and bigger, 1 over x goes to 0. So this is equal to 0. What does that say? The limit as x goes to infinity of natural log of y is equal to 0. So the limit as x goes to infinity of y is equal to e to the 0, right? And e to the 0 is equal to 1. Now recall, y is equal to x to the 1 over x. So what that tells me is that the limit as x goes to infinity of x to the 1 over x is equal to 1. And if the limit as x goes to infinity of x to the 1 over x is 1, we can conclude that the limit as n goes to infinity of n to the 1 over n is also 1. And from there, we can conclude that this sequence converges to 1. And that's how we do example 4. Let's take a look at one more example for this video. And we'll call this example 5. Suppose we have the following. Suppose we have a sub n is equal to, we're going to do this one. N squared times e to the negative n. But this can be written as n squared divided by e to the n. Now, this one is tricky because what you want to do is you want to let y or f of x equal to x squared divided by e to the x. So when you think about L'Hopital's rule, you want to do this on a function defined over all reals, not a discrete function. And we're going to apply L'Hopital's rule here. So if we look at the limit as x goes to infinity of x squared over e to the x. Now, notice if I replace x with infinity, I get infinity over infinity, right? So by L'Hopital's rule, this is the limit as x goes to infinity of 2x, right? I take the derivative of the numerator and divide by the derivative of the denominator, right? Which is e to the x. And if we replace x with infinity, essentially, we still get infinity over infinity. So by L'Hopital's rule, this is the limit as x goes to infinity of 2 over e to the x. And let's note the limit as x goes to infinity of 2 over e to the x is equal to 0. And so what that tells me is that the limit as x goes to infinity of, and we're going to look at this here. So the limit as x goes to infinity of x squared over e to the x is equal to 0. And if that's 0, that implies the limit as n goes to infinity of n squared over e to the n is also 0. And so we can thus conclude that this sequence converges to 0. That's a really, really, really good problem. And that's how we do example 5. And one last question I want to go over with you guys. Let's take a look at example 6. Suppose a sub n is equal to e to the 2n over n plus 2. If we take a look at the limit as n goes to infinity of a sub n, this is the limit as n goes to infinity of e to the 2n over n plus 2. But we could write this as follows. This is e to the limit as n goes to infinity of 2n over n plus 2. Okay? Now, let's come off to the side here. If we look at the limit as n goes to infinity of 2n over n plus 2, this is the limit as n goes to infinity of 2n over, I'm going to factor out an n from the denominator and write n times the quantity 1 plus 2 over n. Okay? Now, these n's cancel. And we're going to apply the limit laws here. So this is the limit as n goes to infinity of 2 divided by the limit as n goes to infinity of 1 plus 2, right? Plus 2 times the limit as n goes to infinity of 1 over n. But this is 2 over 1 plus 0, which is 2. So we did the hard work off to the side, okay? And there's nothing wrong with that, by the way. And so this is equal to e squared. And we can thus say that this sequence a sub n converges to e squared. And that's a pretty good stopping point, so I wanted to do some more examples of determining whether or not a sequence converges or diverges. And in this video, I wanted to mix it up in terms of the types of problems we were going over. I had a couple that involved L'Hopital's rule. I had a problem that involved the squeeze theorem. And I also had a problem that you ended up getting a sequence that diverges. So I wanted to mix it up. Okay, that'll conclude this video. It's on sequences, and we determined whether or not a sequence converged or diverged. Okay, thank you.